that long. You're welcome to get started. Have a good session.
Okay, thanks. So welcome all to the second session of day one of CHESS 2021. Today's session is on masking. So as usual, please follow the ISER guidelines for conference participation. Please post questions on Zulip. Okay. So with that, and then please be muted unless you are speaking. Okay. So with that, first paper that will be presented in today's session is masking in package models, construction, implementation, and verification. So by Marc Gourgeon, Benjamin Gregoire, Maximilian Alt, Tara Paglialonga, and Lars Port. So Marc Gourgeon will be presenting the talk.
Yes, thanks for the introduction. I hope you can see the screen.
Yes, we can.
Okay, great. Okay, yes, our work is on verification of the masking countermeasure. So masking, as we already have seen in the first session, is a countermeasure against side channel attacks. And what we do is that we enable verification of masking security in fine-grained, precise leakage models, which are able to capture realistic side channel behavior encountered in practice on actual physical devices. And we perform this verification not only on algorithms high level, but also enable the verification of this on actual concrete implementation level, to say assembly level. I again need to click somewhere to switch the slides. So masking is a great countermeasure against side channel attacks because it enables to make proofs which rule out entire classes of side channel attacks. The problem is that there's a certain gap between this provable resilience and the actual resilience in practice. To say an implementation of a provable resilient algorithm might still show vulnerable side channel leakage when performed when executed on a physical device. And the reason for this is that physical devices actually have additional side channel leakage behavior and expose additional observable information of an implementation, which is not considered, or often not considered, in the proof, which is usually conducted on, for example, in a paper handwritten. So there's an implementation challenge coming up. One is to actually implement a provable secure algorithm correct, such that the proof holds on this implementation on the semantic level, but also to protect this implementation against this additional side channel behavior caused by the target device. And what we do is that we enable verification to help in solving those two challenges. So our approach is based on a domain-specific language. We have our own language, which we use to represent side channel behavior encountered in practice, and to also represent the implementations which should be verified. And we have implemented this in a proof of concept tool, s-4, which is open source and available to you. And this tool essentially takes a mask implementation, for example, in assembly format as input, and a user-supplied leakage model, which describes what an adversary can observe in practice, and then will perform some technical steps to be able to reuse existing verification tools. In our case, it's maskverif, such that in the end, maskverif will perform a proof of the security of the input, the given input of the maskverif in the end will perform a security proof, proving that this mask implementation is secure under a certain security notion with respect to all the leakage specified in the leakage model provided by the user. Our main ingredient to this is the concept of explicit leakage. We make leakage explicit. We have a dedicated construct in our language which allows to declare that there's a certain value observable by a side channel adversary. So we have this leak statement which allows us to tell that, for example, here the Hamming weight of some intermediate values is observable by a practical adversary and has to be considered in the proof of masking security. And this is very expressive. We can specify lots of different combinations, so transition leakage and arbitrary combinations. And based on this concept, we can model the side channel behavior of instructions, assembly instructions, by using a model. And this is not limited to transition leakage, but in the paper, you will also find that we are able to model leakage across instructions by inserting global leakage state to model the propagation of values. In the end, the model we use, and by the way, this model has been, the characterization which led to this model has been performed by a different set of authors, but we have performed the formalization of this model. So in the end, our model achieved such a level of quality that whenever we were able to prove an implementation to be secure in the model, then we also did not detect any leakage anymore when evaluating this implementation on a concrete device and performing power side channel measurements. And this worked with quite a high number of traces, so 1 million versus 1 million traces, which is, I think, quite a lot. And it also worked for first and second order on multiple devices and across multiple implementations. Nonetheless, it has to be said, this is empirical. It worked for our devices and our implementations and our models. Nonetheless, this shows that we are able to narrow the gap. Verifying and proving security now has an impact on the actual achievable practical resilience in the end. And moreover, using our tool allows to go much further in exploring different implementation strategies of provably secure algorithms. To say we mask the present S-box at first and second order with the goal of reducing the overhead from protecting against device-specific leakage behavior. So we reduce the amount of dummy instructions which have to be inserted usually. And we also came up with new combinations of the underlying gadgets and constructed new gadgets, something you would usually not like to do because it's so hard to implement a new gadget. In the end, we have been able to save so many dummy operations, 70% at first order and almost 90% at second order, that the second order implementation of our present S-box, which we optimized, is using less cycles than the first order implementation, which is based on the usual strategy of composing gadgets. So here you see that it is slower in the end. I think this clearly states that this approach makes sense, and there's a lot to gain by using verification to aid the construction of hardened implementations. And again, the tool is open source, the implementations are open source, the leakage model is open source, and the paper, well, yeah, please go ahead and read it. Thanks.
Thank you, Mark. So I don't, okay. There's one from Jürgen Pulkas. So he says, nice new tool. We observed for a pipelined CPU leakage from an extra direct path from the result of the ALU to its operands in the next cycle. So he asked, can you model this in your IL by storing the name of a variable one in a global state like OPA? Yeah, I'm not sure. So I think so, yes. I mean, the Cortex M0 Plus we have been looking at was also pipelined. And I think what you described, maybe I'm misunderstanding the question, but okay, exactly this global leakage. Again? No, I also have it here on my screen. Thanks. Okay. I mean, it's clearly the way we model these kinds of leakages across instructions is by inserting an additional leakage state like OPA, and then maintaining the operand which has been used in the previous instructions in this additional leakage state, having the ability to express combinations as leakage by the use of leakage statements. So I think it's exactly like you described, Jürgen. Okay, go. So Ein, one of the, sorry.
Right.
Sorry, Sonia.
The second question from Ein. So does your verification tool have false negative results? Namely, is it possible your verification tool reports it is not secure, but the design actually is?
Yes. Yes, we're using mask-per-riff, and I think it's well known that mask-per-riff is extremely fast, scales to very large implementations and also higher orders, but it is not fully precise, and there are cases where mask-per-riff reports that it cannot check an implementation to be secure, and this might be a false negative in this sense. But our approach, so what we did in this paper was actually to reuse an existing verification algorithm, and therefore the whole approach is can be applied to different verification tools. So, for example, we would be able technically, but we didn't perform this, to replace mask-per-riff by, for example, silver, which does not have any false negative results.
Yeah. Okay.
Maybe in the interest of time, we can go
Yeah.
talk, and then if there are further comments, we can address them at a later if there's time.
Thank you very much.
Thank you. So the next talk will be on probing security through input-output separation and revisited quasi-linear masking. It's a paper from Damoun Goudarzi, Thomas Prest, Mathieu Rivin, and Damien Vergniaud, and Mathieu will give the talk. Go ahead, Mathieu.
Thank you, Sonia. Okay. So this paper is about masking and providing formal security for masking. And so our contribution is to provide a new masking composition approach. So just in a nutshell, from a new simple composition property that we call input-output separation, which we instantiate for refresh gadgets, we can obtain full composition security with probing secure gadgets. So the gadgets don't need to be composition secure, they can just be probing secure. And from those iOS refresh gadgets and probing secure gadgets, we can obtain region probing security, which is a composition stronger than probing security. So we also show that an existing refresh gadget, which has quasi-linear complexity, achieves this notion of input-output separation, iOS. And we also revisit a quasi-linear masking scheme. Okay, so we consider what we call standard circuit compilers. So such a compiler applies masking by compiling an input circuit composed of gates on a base field into a new circuit. And this transformation simply replace each wire by n wires that will carry a sharing of the original wire. And each gate is replaced by what we call a gadget. And a gadget simply computes the original functionality of the gate, but unsharing. And we want to achieve this notion of region probing security. So region probing security consider an adversary that can place some amount of probes on all the gadgets of the circuit. And so the circuit is said to be region probing secure if all the wires pointed by those probes can be jointly perfectly simulated without knowing the underlying secret. And so we'll say that the circuit is R region probing secure, where R is a rate parameter, and it means that each gadget should tolerate a portion of R leaking wires. So it can tolerate R times the number of wires in the gadget as a number of probes. So why do we care about region probing security? So that's because we have this reduction. So the region probing security implies random probing security, which in turn imply noisy leakage security. And those reduction somehow preserve the leakage rate. So it's approximately equal for each step, where we have some scaling by a small constant factor. But yeah, in general, it keeps the security. And the nice thing is that this noisy leakage model is more realistic to capture power and electromagnetic leakages. Okay, so let me now present this notion that we introduce of input-output separation. It's pretty simple, actually. It just says that any T probes on a gadget can be perfectly simulated from the knowledge of T input shares and T output shares. So that's just what it says. So in order to show that a gadget is iOS, we have to show that for any set of T probes, we can design a simulator that on input, T input shares and T output shares will produce a perfect simulation of those T internal probes. And we can show that this notion is actually weaker than the previous composition notion. So assuming that the gadget is uniform, which means that the gadget produces a fresh output sharing, then this notion is weaker than, so SNI gadget or NI gadget or PNI gadget would also be iOS. But the converse is not true. So it means that we might reach more efficient construction by only requiring iOS. Okay, so our composition approach is also pretty simple. So the principle is just to introduce a refresh gadget on each connection between any two gadgets. And if this refresh gadget is iOS and uniform, we can show that the full composition is region probing secure, assuming that the other gadget, the operation gadgets, are simply probing secure. Okay, so we also instantiate this approach by showing that this refresh gadget, which is due to Bastistello, Coron, Proof, and Zetoun, actually achieves iOS. So just in a nutshell, this refresh gadget consists in applying log n layers of refresh blocks. So the first block considers the full input sharing, then the sharing is split into two blocks, and we have two independent refresh blocks, and so on. And so we just provide a small variant of this gadget. Actually, we only require half of the layers. So we require log n layers to achieve iOS, whereas the original gadget relies on 2 log n layers to achieve SNI. And we also generalize it to what we call V-sharing. So a V-sharing is just a generalization of a standard Boolean sharing or additive sharing, where the shares are multiplied by constant coefficients. And that's what we use for the quasi-linear masking scheme that we revisit. Okay, and so we revisit this quasi-linear masking scheme that we introduced with Damon Goudarzi and Antoine Joux at Asia Crip 2018. So this masking scheme enjoys quasi-linear complexity, so it requires n log n operations, and achieve random probing security, and it's defined over some fields with a special form, which allow to apply the number theoretic transform on those fields. And what we do in this paper is to generalize this scheme to any form of base field. We also generalize the proof to region probing in the region probing model, which is more general because it implies the random probing model. And we also patch a flow in the original proof by using this iOS approach. So the flow was due to the refresh procedure that we use in the first scheme. And this is basically a shortcut in the proof. It doesn't lead to a concrete attack, but yeah, the proof wouldn't hold using this former refresh gadget. Okay, so just to give a sense of how we obtain the security. So if we look at the multiplication gadget of this scheme, we have some shareWise blocks. So the scheme is also composed of addition blocks and subtraction blocks, which are shareWise. And we have FFT blocks. And so we can show that the FFT blocks are probing secure on large field, but it's an open problem to have the probing security on small fields. But composing all those probing secure blocks and refresh iOS refresh, we get the composition security. I might be running out of time, so just quickly, we apply the scheme to AES and MiMC. And we see that thanks to quasi-linear complexity, we scale with the number of shares to more efficiency. And yeah, I think I can stop here. Thank you for your attention, and I'll be happy to take any question.
Thank you, Mathieu. Maybe a quick question from the chat. It's from Amir Moradi. So Mathieu, apart from the soundness of the underlying theory of this model, can you comment on its practical relevance? I mean, why should we consider this model instead of classical probing model for security of implementations in practice?
So, so the nice thing with this reduction from Duke, Dembowski, and Faust is that from probing security, we have this reduction to the noisy leakage model, which is arguably more realistic to capture power and electromagnetic leakages. But if we consider simply the T-probing security model, then this reduction is not tight at all. And if we want a tight reduction, we have to consider a model where we allow the adversary to get some leakage and then some probes on all the gadgets on the circuit. So this region probing model is actually more realistic than the standard probing model.
Thank you, Mathieu. Maybe we'll continue with the next talk.
Yes. So the next talk is on redundant code-based masking revisited. So by Nicolas Coste and Martin Stam. Nicolas Coste will be presenting the talk.
Hi. So if you cannot hear me correctly or if the slides are not moving, just tell me. So I'm Nicolas Coste. I'm a PhD student at Simula UV, and yeah, this is joint work with my supervisor Martin Stam. And I assume by now you are all familiar with the concept of masking, but this talk is going to focus on polynomial masking, which was introduced by Prof and Roche in 2011. And the idea of polynomial masking is that basically you use Shamir sequence sharing scheme. So you generate D random variable, where D is the masking order. And those define a random polynomial with a value at 0, the value you want to mask. And you evaluate that polynomial on a public set of points, n points, that makes n shares. So you can have more shares than you need to reconstruct. And the main claims from the original paper was that if n is minimal, so you just have the amount of shares that you need to reconstruct, polynomial masking should leak less than Boolean masking when only taking in account the share. And if you have more shares than you need, so if n is over d plus 1, you have what you call redundant masking. And those extra shares then can be used in an MPC fashion to defeat glitches and fault attacker. So it would be nice to unify fault attack and masking. Now, the question that we asked ourselves in that work is that because we introduced those two extra parameters, the sets of points on which you evaluate, and the fact that you have redundant leakage, what is the effect of those parameters on the general leakage of the scheme? And that was the question that we asked ourselves. And we started with redundant leakage. And redundant leakage was already the topic of a paper in 2018 by Shaban, Magrema, and Proof. And they concluded at the time that the attacker was unable to exploit redundant shells in a successful attack. However, we discovered that they make a mistake in their distinguisher. And to highlight the error that they make, I just picked a degenerate case, let's say, where D would be equal 0. So we don't have any masking. We are just repeating the secret twice. So just imagine that as we are running the algorithm, the secret is repeated twice in all the operation. And what would be expected is that we would have basically two times the same value with independent noise, so a nice 3D Gaussian. And if you use their formula, you still have a dependency for some reason on the interpolation point, even if you don't have even if you don't have masking at all, and you end up with this weird Gaussian mixture. And this also extends when you have a redundant masking, basically. So their conclusions are a bit up in the air. So we redid the investigation. So we used Hemingway model experiments, and we heuristically determined the amount of trace that you need to reach a 90% success rate. And like you can see on this graph is for D equal 1, so the minimal amount of shares to reconstruct is 2. we are giving the adversary first 2 shares, then 3 shares, then 4 shares, and we see how fast the adversary is able to reach the success rate in amount of trades in log scale. And you can see that as n is increasing, the amount of shares required to reconstruct is getting lower and lower. So there is a clear security degradation, and the adversary can always exploit those redundant shares. So there is a trade-off in that scheme. If you want to protect against faults, you are basically enabling an attacker to be more efficient if he's just using regular session attack. Now we move on to the other result, which is about sets of points. So we identified 2 sets of points that should be avoided when using that scheme because they lead to degraded leakage. And then the first one is sets of points that lead to an equivalence to Boolean masking. So I'm going to give you an example. We identified more of them in the paper, but if you have the parameter g equal 2 and n equal 3, so you need 3 shares to reconstruct, and you have the sets of points a, b, and a plus b. If you compute the shares, you can see that if you sum them together, and by summing, it's in the finite field, so bitwise XOR, you see that you get back your secrets. So basically, you ended up in Boolean masking, even though you are doing polynomial masking, because of how you pick your sets. So we also did the amino weight experiment, and the results are exactly the same. So it's really an equivalence to Boolean masking. It also, let's say, debunked the claim of the original paper that polynomial masking is more resistant than Boolean because it depends on the sets of points. Another set of points that we identified, which is the final result I'm going to present, is what we call quasi-Boolean sets. And it's more or less the same idea as the previous one. You still have this, I'm still going to give you an example with the sets of points a, b, and a plus b, but this time d is equal to 1. So you only need 2 shares to reconstruct, but you still have this alternative to reconstruct by summing the 3 shares together. And this extra structure leads to more leakage. So in the graph, you can see that in the blue area, it's all the non-quasi-Boolean sets of points that we investigate in that work. Some of them, obviously, we didn't do all the sets, so some might be slightly out of the blue zone. But in black, you have the quasi-Boolean one, which is clearly much worse than the blue zone. And one of our conjecture is that the blue zone is going to go over the second order Boolean as the noise is increasing, but the black line is probably going to be bounded by second order Boolean. But that's just a conjecture. So that was the 3 main results I had to present. Our analysis in the paper is made using a link between coding theory and secret sharing. And I refer to you for the paper for the analysis and the proof of what I showed. So yeah, the references I used, and I'm happy to take any question.
Thank you. I don't see any question yet. If there are any questions, we'll get back to you. Thanks.
Okay, should we continue with the next talk, though?
Oh, yes, we can.
Okay. Okay, so the next talk is about information leakage in code-based masking, a unified quantification approach. The paper was written by Wei Chang, Sylvain Guillet, Claude Garlet, CM Ménager. Sorry, and the speaker will be Wei. Please go ahead.
Wei, if you're speaking, you're still muted. We cannot hear you.
Sorry, can you see my screen?
Yeah, we
Yes.
can, and we can hear you as well. Thank you.
Okay, thank you. Thank you for introduction. I'm Wei Chen from Telecom Paris, and I'm privileged to present our work on how to quantify information leakages in code-based masking. In the previous talk, I presented attack-based evaluation. On the contrary, in this talk, we will present how to quantify leakages by some leakage evaluation metrics like signal-to-noise ratio and neutral emission. So as we know, the Boolean masking is well-studied countermeasure to protect cryptographic implementations. So typically in Boolean masking, we have X be the sensitive variable and Y be the random masks, Z be the masked variable. We can have the following encoding. Actually, we can express it as a coding theoretic form on the left. So basically, the G and H are to generate a matrix of to code C and D. We can say that the only in Boolean masking, G and H are only in Boolean matrices, binary matrices. And on the right, we present as example of inner product masking. And the only difference is on H, where the first column is alpha 1 to alpha t. So we have a t equal to m minus 1. So in general, the two examples can be generalized from a coding theoretic perspective. So let z equal to xg plus yh, where x, y, z are the same as the previous, and G and H are two general matrices. So in the generalized code-based masking, the only condition is that the two codes C and D are there is only one zero code word in their intersection, and if there is no redundancy, n equal to k plus t, and if there is a redundancy, n greater than k plus t, as in previous talk. So here is a brief history of code-based masking, and including other examples like Boolean masking, inner product masking, linkage squeezing, and also polynomial masking, which is presented in previous talk. So in 2020, the generalized code-based masking is proposed, and it actually generalize all these masking schemes. And the connection between different masking schemes are presented in this figure too. So on the left part of the figure, there is a ratio, which including Boolean masking, IPM, AES, and DSM, and then go to generalized code-based masking. And on the right, it's polynomial masking. When there is the intersection with the right side, it must be n equal to t plus 1, which means there's no redundancy. And two problems arise how to measure information leakage in different schemes. And secondly, for each scheme, how to choose the optimal code, or choose the public point set as in polynomial masking scheme. So in this work, we present two main results, which is based on single to noise ratio for hemi-weighted leakages, which is clearly connected to two coding theoretic parameters: the due distance of the code D, and the B prime, which is connected to both code C and D. And from an information theoretic point of view, we have a large result regarding the mutual motion. Similarly, we have this part is connected to the due distance, and we call this B prime D is the adjusted Casey number. So we can visually see the impact of two parameters. By reducing D, we can reduce the information leakages that when the noise level is lower, and when the noise level is increasing, we can reduce the leakages by increased D. So actually, the due distance is equal to the slope of the visual motion in log-log representation. So next, we apply our theoretical result to 3-1 SS-based masking. So we have G and H as follows. And in the encoding, we only have one random mask, which is first order masking scheme. And we can say that by using our mutual information, we can estimate the mutual information when noise level is high. And meanwhile, we can use the two parameters, the due distance and the adjusted casing number to choose the best parameters or the best code for code-based masking. So basically, clearly the black curve represents the best one, which has the maximized due distance and minimized B prime D. On the next, we can show that we can do an exhaustive search on all the possible candidates of parameters. Here we show the best one is on the right side. So comparing to the state of that, we can extend the existing work in two directions. First thing, we show the best cases of the linear code or the best set of public parameters, which are recommended to use in practice. And secondly, we give the worst cases of linear code that should not use in practical applications. Actually, we believe that our results actually answers the question proposed in previous talk, which means that we can show that which code or which parameters are the best in code-based masking. Next, as in the previous talk, we have
sorry to interrupt. You just have a minute to wrap up. Could you please quickly do that?
Okay. So as in the previous talk, we can show that from information static point of view, more shares, as in the red one, leaks more information, which is advantageous to attacks in practice. So basically, we have a coding static approach to quantify the information leakages in code-based masking. That's it, and thanks for your attention.
Thank you, Wei. We are running a bit out of time, but a quick question from Martin. Can you also use your method to compare different field representation with respect to their leakage profile?
Sorry.
Do you want me to repeat?
Leakage profile?
Yeah, can you also use your method to compare different field representation with respect to their leakage profile?
I'm not sure what is the leakage profile. So.
Okay, so maybe you can go back to Martin on the Zulip chat.
Okay.
That you can answer directly, or we can continue after all the talks. Okay.
Okay. Thank you.
Thank you for your talk.
The next two, the authors of the next two papers are Ayn Raisi, Shah Mirzadi, and Radi. Ayn will be presenting both the talks. The first paper that will present is Reconsolidating First Order Masking Schemes, Nullifying Fresh. Over to Ayn.
Okay, thank you for the nice introduction. I'm Ayn, and this is a joint work with Amir Moradi, and we are from Ruhr University Bochum. This paper, we focus on the first order security and try to remove fresh randomness. So, okay. So I start with the glitch extended probing model, which is dedicated to the hardware implementations. So in this model, when a probe is placed in a combinatorial circuit, it propagates backward up to the last synchronization point. So for example, in this circuit, if the attacker probes, let me show this pointer. Okay, if the attacker probe this wire, it propagates backward, and he has information about all these input variables. So under this model, some masking schemes is secure. The first one is a threshold implementation based on 3 well-known properties. And then we have D+1 sharing, which uses the minimum number of shares. I brought a simple first order 2-input AND gate secure design here. So the general structure is divided into 2 parts. The first part is component functions, and then we have the register layer, and then the last we have a compression layer, which several component functions are compressed to generate output shares. So in this case, we need a single bit fresh mask to ensure security, but we know for some Boolean functions, we don't need any fresh mask. So for example, for a simple function like this, RB plus C, this construction is secure and we need no fresh mask. And if we replace the C with B, the design remains still secure under glitch extended probing model, and the output shares are still uniform. So based on this, we presented the first 2-share mask AND gate without any fresh mask by inverting the A input variable or input variable A. So this motivated us to present an algorithm to find 2-share mask design of a Boolean function with no fresh mask. So the application of our technique to 3-input AND gate led to many solutions with no fresh mask. And then we applied our algorithm to middle S-box and present S-box. Note that the coordinate function of these S-boxes is at most cubic. So we found many solutions for both of them with no fresh mask and using only 2 shares. And for prints, both S-box and S-box inverse are used in the encryption and of course decryption function of prints, but our algorithm didn't find any solution which is jointly uniform. But if you consider 3-bit of outputs, it's still uniform, but when we add the 4th one, then it's not uniform anymore. But still we implemented this, and basically we implemented the S-box and S-box inverse and the round function, and we did this FPGA evaluation, and we didn't see any leakage. And we think this is because of a diffusion layer of prints, and namely the mix column of prints, because it doesn't mix the output bits of an S-box, and basically it mixes different bits from different S-box, and we think it has a key rule, and the detection, the leakage is too small to detect, at least in our experiment. And as a last case study, we investigated AES S-box, and we used tower field approach. This is the inversion, and we have we basically integrated the multiplier here with these 2 XORs and the square function into one function called a square multiplier, which is an 8-bit to 4-bit function. We have an inverter here, which is a 4-bit to 4-bit function. We have 2 multiplier at the end. And we found several solutions for each of them. And we presented 2 basically different design. The first one with 1-bit fresh mask, and the other one with no fresh mask at the cost of higher area overhead. So as I said, the output of the multiplier is uniform, I mean, each of them, but when you consider both of them, again, it's not uniform. So we again use the AES diffusion layer and basically mix column. So basically we decompose the mix column into beta function and the mix column prime here, and put a register layer in between, and we designed and implemented a byte serial implementation of AES, and we did again the FPGA test, and we didn't see any leakage. So again, we think the diffusion layer has a key role in this observation. So in this paper, we presented a methodology to realize first order 2-share mask realization of Boolean function with no fresh mask. And we have investigated several block ciphers, and our designs are first order secure with only 2 shared with no fresh mask and without applying changing of the guards. So thank you for attention, and please ask your questions.
Thank you, Ayn.
Sure.
I don't yet see any question on Zulip.
Okay.
Maybe you want to continue with your other talk and wait for the questions?
Sure. So the next one.
So your second talk is about second order SCA security with almost no fresh randomness. And it's a paper written by Ayn, also Amir Moradi.
Okay, thanks for the introduction again. And I just start with, so it's not switching. Okay. Start with the algorithm here because I already talked about the basics in the last talk. So I'm going to explain the algorithm through a simple example. We have a 2-input AND gate here, and each input variable is represented by 3 shares, which is the minimum number of input shares for second order security. And in this way, we have 9 shared monomials. So this forces us to use, so I need laser point. Okay, so we need at least 9 component functions. So basically A0, B0 goes to F0 and A0, B1 to F1 and so on. So if we assume F0 to F2 are compressed to generate the first output share, and F3 to F5 are compressed to generate X1 and the second output share, and the rest are compressed for the X2, the general structure of design is something like this. So we first focus on this part. The circuit is generating the first output shares and trying to find a second order secure solution. And then we do the same for the other 2 parts. And of course, at the end, we check whether the whole construction is second order secure and the output are uniform or not. So F0 has A0 and B0 in its input list, and we can construct 4 different Boolean functions with A0, B0 and quadratic Boolean function. So we need a combination, and we can do the same for F1, F2 to F8. And we need a combination which is probing secure. Namely, if we put 2 probe on 2 different component function, we should check whether it's secure or not. But because of second order non-completeness, we didn't check in our algorithm. So we should check whether one probe is in one of the component function and one at the output of the XOR. Because of the glitch extended probing model, is expanded to 3 different probes here, and we should check these 4 set of probes. And of course, the second one can be on F1 or F2, and if we found any solution or any combination, we check whether X0 is a balanced function or not. Basically, it means it has as many as 1 as 0 or not, because it's a necessary condition for achieve uniformity. So once we found a solution, we save it in a set. So we have F0, 1, 2. A set contains the second order secure elements, and we do the same for the next 2 parts. And here we check whether the whole construction is secure or not. So basically, we have to do more checks. One at X0, I mean the output of the XOR, which is extended to 3 probes, and the other one on F3 or F4 or F5. And the other possibility is the second probe is on X1, which is again extended to 3 more probes, and we should check these 6 probes for the security. So if we found the solution, we add the third one and do the same checking again. And if it was secure, then we should check for these 2 parts. And if there was any solution, we check whether the output is uniform or not. So as you can see, there is a lot of programming, a lot of checking and the computational complexity is pretty high because the search space is pretty high. So the application of our technique in to two input AND function led to no result without any fresh mask and with a single bit fresh mask, but we found many solutions for with two fresh mask bits. And for AND XOR, we found many solutions with no fresh mask. So this motivated us to study and investigate some case studies. So at first we focused on Ketchog, which uses a 5-bit SPOX with quadratic coordinate functions. And we designed 2-share and 3-share round-based implementation of Ketchog with no fresh mask, basically with first order and second order one. So for the first time, we designed such a construction. And as you can see, our designs don't need any fresh mask while maintaining the area overhead. We already applied our algorithm to several block ciphers, and here I brought an example of Midori, but the rest is also the same. We decompose the SBox into some affine functions and quadratic bijections. So as we can see here, we have input affine. The result should be stored in the register. We have F and G here, which are quadratic bijection, and the important things here is injecting fresh mask at the interconnection. F and G are second order secure by itself, but when we compose them, we need a fresh mask to ensure the security. So in this paper, we proposed a methodology to achieve 3-share second order secure implementation of quadratic bijection and quadratic functions. For the first time, we presented first order and second order secure designs of Ketchog with no fresh mask. And we also investigated several block ciphers and presented the second order secure mask version of them. So thank you so much, and please ask your question if any.
Thanks a lot. So there is a question on the Zulip chat for this second talk. Did you only consider partitioning the 9 functions in 3 groups of 3 functions, where in each group always the same AI is used? Or did you try also the configurations, maybe even of different order?
Yeah, this is a nice question. Yes, this is not the only possibility, and we already considered other possibilities. Yes, that's right. I just mentioned one possibility, but yes, of course, we can use different coordinate function to compress and check. There are a lot of checking. Yes, we consider all of them.
Okay, and I also have a very quick question. How far can we go? Can we try with the 3rd order, 4th order, or is it too complex to analyze?
Yes.
I also wanted to ask the same question. Thank you, Sonia.
Yes, the search space will be too large for 3rd order and 4th order one. I mean, even for 2nd order, the quadratic bijection is too large. I mean, we need a lot of optimization, a lot of programming. We need good actually servers to search. So yeah, I mean, probably for 3rd order, at least today, it's not possible.
Okay, thanks a lot, Ayn. So I think we will stop this session now because we are running a bit out of time. But we would like to thank all the speakers of this masking session. Thank you all. And